Here we're going to look at a few conceptual questions to review some of the material that we've already talked about in the class. So these are just multiple choice questions. And a conceptual question means that, well, it sort of sounds like it's something about intuition or having sort of a pictorial or qualitative understanding of the subject. But actually these questions should be understood and answered exactly through the precise definitions that we've made, exactly through the techniques that we've learned. It just usually means that we're not going to be finding some sort of quantitative numerical answer. So I don't want you to think that these conceptual questions are sort of a different subject matter than what we've already looked at. However, they do seem to require a different skill set that you need to develop in order to answer these kind of questions, rather than just sort of answering numerical problems where you're solving a problem with your calculator. We'll see how it goes. I've divided up into 3 sections, so there's a few questions on just vectors, a few questions on kinematics, the definitions that we set down, and then a couple questions on how to analyze position versus time graphs. And I'll go through and show you each of the questions. You can pause and answer the questions, and then we'll come back and I'll go through the solutions. And as I said on a previous lecture, if you can, it might be good to find a neighbor, a friend, who will do this with you, and you can discuss the questions. Best to answer the questions first, then discuss them with someone, and then come back and take a look at the solutions. We'll start out with 3 or 4 questions on vectors. Here's number 1. Again, you can pause. Here's number 2. Oops. Number 3. Number 4. So, this question. Which of the following is true? And it could be that more than one thing is true, so let's take each one one by one. If any component of a vector is 0, the magnitude must be 0. Well, we know what these words mean now. Components, these are the numbers that you get when you place a vector in a coordinate system. And magnitude, that's the length of the vector. And we also know that if you have a vector v, then the magnitude of v given its components is going to be the x component squared plus the y component squared square rooted, plus z component squared if you're in more dimensions. So is this statement true? Well, no, because I could have said, well, this vector doesn't have any y component, which of course would mean that the vector looks like this. Does that vector have a 0 length? Is its magnitude 0? No. It has some length. We can see that here. So that one is definitely not true. The components of a vector are always positive. Well, that's certainly not true either. If we look at, for example, this vector here, remember how we find components. You go back to the axis, and this is what we would call v sub y, and then you go back to the axis, and this tick mark is what we call v sub x. Well, just based on this coordinate system where I put an arrow in the positive direction, you can see that v sub y is a positive number, but v sub x, this tick mark, is on the negative x-axis, so that's a negative number. So certainly vector components can be negative. The absolute value of each component is less than or equal to the magnitude. Well, let's take a look at it. So is it possible that we get a component which is greater than the magnitude? Well, I don't think that that's possible. So let's let's imagine that our vector sits only along one axis, then its component here, its only non-zero component Vx, would be equal to its magnitude. You can see that, right? The length of the vector is exactly equal to this number right here. And if I move that thing off of the x axis, then the x component would get smaller. So let's just show that. If I keep it the same length, but then move it off the axis, well, you can see that the x component is now a smaller number, and now there's some y component number. And so these numbers are always less than the magnitude. So what's true is that the components are always less than the magnitude. So the absolute value of each component is less than the magnitude is absolutely right. So let's say yes for that one. The magnitude is equal to the sum of the components. Well, we already looked at what the magnitude is in terms of the components. That's not true, so this one is false. So it's only C that is true. Three vectors have equal magnitudes. Their lengths are equal, but A points north, B points west, and C points south. So let's just draw a coordinate system. So we usually write this as an XY, but we could also call it a north or an east-north coordinate system. What direction does D, which is A plus B plus 2C, point? Well, let's draw out the vectors first. So A points north. Here's A. B points west. Here's B. And C points south. Here's C. So what is A plus B plus 2C? Okay, well, let's just try it. So we'll give ourselves a new coordinate system. A points north. B, add that to it, meaning put its tail at the head of A, points west. And 2C, 1C, 2C. And where is the resultant? Where is the D vector? Well, it goes from the beginning to the end, from the first tail to the last head. That's our D vector. So what direction is that? Well, this is west and this is south, so that's exactly southwest. So our answer is F. Two vectors have equal magnitudes, but A points north, B points west. What is A minus B? Again, here's our A vector. Here's our B vector. So what is A minus B? Well, A minus B, remember, is A plus the minus B vector. And what is the minus B vector? It's the opposite of the B vector. So this vector here is the minus B vector. And now we just have to add A and minus B. So here's A, and here's the minus B vector, and the resultant goes from the beginning to the end. That's our C vector. So what is that? Well, that's northeast. Where's northeast? B. Last question. Two vectors have equal magnitudes, but A points north, B points west. What is the component representation of A plus B? So, and it says treat north as positive y and east as positive x. So this is usually called the y and the x, but we'll also call this the north and the east direction. So we have A points north, and B points west. So what does C look like? Well, let's do the graphical addition. We can do this in two ways. We can do graphical addition, so A plus B is C, and you can see what the components of C are, because we can drop back to each axis. So there's c sub x, and there's c sub y. So c sub x is a negative number, and c sub y is a positive number. You can see that c sub y is equal to the length of A, and c sub x is equal to the length of B. They're both 1. So we see that c is equal to cx, cy. Well, x is minus 1, and y is plus 1. So our answer then is D. What's the other way that we could do this? Well, we can find the components of A and B immediately. So A, that one only points along the y-axis, so it has a 0x component and a 1y component. And B, that one points along the negative x-axis, so it's minus 1 comma 0. And then if you add those two things together, you get minus 1 comma plus 1, which is the same thing we got here. So this is what we call the algebraic method of solution. You find components, and this is what you call the graphical method of solution. You analyze the vectors graphically, and then somehow you find numbers out of them, either by finding a component in the end or by doing some geometry, trigonometry. We'll move on to a couple of definitions about kinematic quantities. So here's the first question. Pause the video. And here's the second question. And I think that's all, so let's come back and we'll do the first question. Displacement versus distance. So let's, before we even look at it, let's just remember our definitions of these things. Displacement we called delta r, and it was equal to r final minus r initial. And in order to define displacement, we need to know what r is. It's the position, and that's relative to a chosen origin, meaning to a chosen coordinate system. One last little piece of it, remember, if you have two position vectors, r initial and r final, then the displacement, because of that subtraction definition, goes from the first one to the second one. That's the delta r vector. So that's a little bit screwed up there. There's the delta r vector. Okay, so that's displacement. What is distance? I don't think we actually wrote down a definition of distance, but distance is simply the distance traveled. So remember, it was part of the average speed definition, total distance traveled over total time. So basically you have to look at the path and measure out along the path with a ruler how far you travel. Okay, so an object goes from one point in space to another. After it arrives at its destination, the displacement is greater than or equal to, always greater than, dot, 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 all of these things, than the distance traveled. So which is larger? So let's just make a trip. So we'll do it 2 dimensions, and you'll see that that certainly means that it would generalize to any number of dimensions. So let's draw the path in space, meaning the set of all positions that the object takes on the way from A to B. We could go straight from A to B, but why do that? I mean, certainly with driving a car, you can't always go straight. Sometimes you have to take the places where the roads are. So here's a path that one might take from A to B. Okay, what is the displacement from the beginning to the end? Well, the displacement, as we saw up here, simply points from the initial point to the final point. Now we could have put a coordinate system over here and have a position vector here and a position vector there, but the delta r vector, the displacement vector, will always point directly from A to B. So that's our displacement vector. Now the question was, how does the magnitude, oh, it should have said the magnitude, otherwise you can't answer this question. So the magnitude of, I guess it should go here, right? the magnitude of its displacement. Otherwise, you can't compare a vector to just a number. So the magnitude of its displacement is either greater than or equal to the distance traveled. Well, you can see from this picture that the distance is much longer than the length of the displacement vector. Now, I could have taken a straight path, and in that case, the distance would be equal to the displacement vector. So we see that the length of the displacement vector is always less than or equal to the distance traveled. So is that one of our answers? The displacement is either smaller than or equal to, it looks like it's D. So that's our answer. Okay, two more definitions, average velocity and average speed. This should probably say average speed. So what is average velocity? Well, that was a definition. And remember, it was a vector. So it was the displacement vector over the time of that interval. Remember, displacement goes from one point to another point. There's a time associated to the initial and to the final. So delta t is just the time difference between those. Average speed was something different. And we'll just write it as average speed because we don't really have a variable for it. And it's the total distance traveled over the total time, which we might write as d over delta t, something like that. So the question is, over the time interval from 1 week ago to now, which is larger, the magnitude of your average velocity or your average speed? This time I wrote the question correctly. We're comparing the magnitude of the vector, which is the average velocity, to the average speed. Well, I'll just do it for me. It's a Monday morning, and I'm sitting in my home. And a week ago, it was also a Monday morning, and I was also sitting in my home. So let's look at what I've done from Monday to Monday. Here's my home. I did go to school out at Grand Valley State University. And so my path from Monday to Monday might look something like this. I went to school, I went back home again, I went to the grocery store, I went back home again, I went to school, I went back home again, blah, blah, blah. I went to school a bunch of times last week because it was the first week of school. So the total distance traveled was quite long. I don't know, might be measured on the order of 100 or more miles. The total time was a week. So it's 100 miles divided by a week. That's my average speed. We could calculate that in a moment, but you'll see in a second we don't need to. My average velocity, well, I started out at point A, and today I am also at point A. So point B is point A. So my displacement is almost exactly the zero vector because I did not move. I did not change my position in space from the beginning 1 week ago to the end. I'm at exactly the same place. So for me, delta r magnitude is equal to 0. The vector is 0. So which one is larger? Certainly my average speed. And I imagine it's the same for you, because remember, the distance traveled is always greater than the magnitude of the average of the displacement. So even if you, for example, between Monday and Monday went from Paris to Grand Rapids and did almost nothing else, then they would be equal. And if you diverged at all from a straight line path, then the average speed would be greater. Now we'll look at a few questions analyzing position versus time graphs. So again, you can pause, take a few minutes to answer, maybe find a friend to compare your answer with. We have the first one, second one, third question. And that's it. Okay, so these are all labeled as position versus time. That means usually the x position, for example, versus t. So these are x versus t graphs. They might also be y versus t, but they're not vectors. They're just one component direction of the possible vector quantity of the position vector r. So how do you analyze these things? Well, let's remember the key points. If we have an x versus t graph, then it's related to the velocity versus time graph. And the way that it's related is that velocity, well, average velocity, remember, was equal to the change in position over change in time, which means that the x component of the average velocity is delta x over delta t, and that's just the slope. So if you take 2 points, then you draw a line connecting those points. That's your average velocity. The slope of that line is your average velocity. If you want to find the velocity at a specific moment in time, then you find the tangent line to the curve. So let's just draw some example like this. If I want to find the average velocity, or the velocity at, for example, this moment in time, right here, well, then I draw a point on my graph there. I find the tangent line, the line that's exactly parallel to the curve at that point. I find the slope, and you see, well, that is a negative number. In fact, it's probably the most negative number that we have, and I would plot the velocity there. There are a couple easy places to find the tangent line slope, and that's where it goes to 0. So we know that this is a 0 value in velocity, and this is a 0 value of velocity. And prior to this point, the slope was positive, so I can draw a positive velocity here, negative, positive again. So that's what the velocity graph looks like. So the key questions are having to do with the slope of position versus time being the velocity. Now let's try and answer the question. So a person is initially at point P here. They stay there for a moment, and then they move along the axis to Q. They stay there for a moment, and then they go quickly back to R, where they stay, and then they go slowly back to Q. Okay, so there are 2 things we should consider here. One is sort of how things are changing with respect to time, and in particular, if you stay somewhere for a moment, then that means that your position is not changing, delta x is 0, while the time is changing. That means the v is equal to 0, that means the slope is equal to 0. So every time it says stay, we should see a constant position, a slope of 0 and a value of position that remains the same. So initially at point P, you stay for a little while, so there should be a constant slope at the beginning here, and we see that on all the graphs. Okay? Now, the graph tells us a little bit about where the person is. They're initially at 3, so that should be a positive number that they're starting at because of the way that it's located. So I think that we should definitely exclude this one and this one, because in the first of those, it's a negative position, and we were told they're on the positive coordinate axis, and here it's basically a 0 position, and that's certainly not true. Okay, then the person moves along the axis to Q. So which way are they going? They're going backwards. So if they're going backwards, then delta x is going to be negative. The v is negative then, because delta t is always positive. Time always moves forward for us. So that means a negative slope, or simply you can see it going from some large position to some smaller position. So staying where they are and then going backwards. Okay, that looks fine. However, this one landed at 0, and we see that Q is not 0, so we can already exclude this one. The next one, staying where they are, going backwards. Yeah, that looks okay. Staying where they are, going backwards. This one went negative, so not that one. And then staying where they are, going backwards. That looks fine. So we're left with two. Hopefully we can exclude them. So in this case, right after Q, she runs to R, stays there, and then goes slowly to P. So in both cases, she's increasing her position, so that works for both of these. But the difference between these two graphs is that there's a large slope, a plateau, and then a small slope, whereas here there's a small slope, a plateau, and a large slope. So the velocity here is larger than it is here. So this would be running quickly, stopping, going slowly. This would be going slowly, stopping, running quickly. So number 2 is the correct one. A train moves along a long straight track, and the graph shows position as a function of time. So what is happening to the train? Well, let's redraw this like we were doing before in terms of the position and the velocity graphs. So this is x versus t, and this is v sub x versus t, which is telling you what the slope is. So it looks something like this. So it's sort of nearing a zero slope at the end, although it doesn't look like it ever reaches zero. So at no point on this graph are we going to find a zero velocity. The slope here everywhere is positive, so we should have all positive numbers. And yet it's headed towards zero. So if we extended this a little bit further, we might get to zero. So probably a good value of the velocity would be, well, let's draw a tangent line at the beginning. At the beginning, there's some positive value of the velocity. So we could draw that as just some positive number. And then it gets smaller and smaller as time goes forward. So we could draw it sort of like this. It doesn't quite reach zero, but it goes down. Okay, so what's happening to the train? Is it speeding up all the time? So speeding up means that the magnitude of the velocity is getting larger and larger. Well, this is a positive component, Vx, and the single positive component is definitely not getting larger. It's getting smaller, it's going to zero. So that's not true. So it's not speeding up. It's slowing down. Well, that means that the magnitude of the velocity is getting smaller. That actually is true. You can see that in your graph, that the v is getting smaller and smaller. Speeds up for part of the time, slows down for part of the time. We don't see any evidence of that. If it sped up and then slowed down, then you would see the graph getting larger and then smaller again, and that would require that you have, well, what would it require? It would require that you have a large slope in position versus time and then a small slope. Sorry, it would require that you go from, so speeding up means that you go from some value of velocity to a larger value of velocity, so some value of velocity to a larger slope in the position versus time, and then back to a smaller slope. And here we only have a decreasing value of the slope. Moves with a constant velocity, well, that would be a straight line here, and a straight line, a horizontal line on velocity versus time, means that the slope, x versus t, is the same at all moments in time. And that line would be a straight line. We don't have that, so that's not true. So none of these other ones are true, and we have b slows down all the time. Final question. This is position versus time for two trains. What's true? Well, let's look at both of them. So for train A, what's happening to its position versus time? Well, it's just a straight line. What does that mean in terms of velocity? It means that It means that the slope of position versus time is the same at every moment in time. So if I plot the slope numerical values on v versus x, it will be some positive number that doesn't ever change. That's A. What about B? Well, B, initially, it has some slope, and that slope, you notice, is larger than the slope of A. So initially, B is going to have some value of velocity which is larger than the velocity of A. And then at some moment, it looks like the slope matches that of A. And that happens somewhere like in the middle time. So at some moment, the value of the velocity of B is equal to the velocity of A. And then at the last moment, that slope is definitely smaller than the slope of A. So it's going to look like this. Okay, does that help us? At time tb, so at this final time, well, what happens with these two graphs? What's happening at tb? Well, the position graphs are intersecting. So that means that they are at exactly the same place on the ruler. They're passing each other at that moment. They're also at the same place at the very beginning. The B was going faster at the beginning, so it's like they started out together, and then B went ahead of A, and then as B slowed down, A passed. So this is sort of like the tortoise and the hare. The tortoise, A, is moving slowly but constantly. The hare is going fast and then gets tired and takes a break and a snack, and eventually the tortoise wins. So at time tb, both have the same velocity. That's definitely not true, because if we look at this point, you can see the slopes are different. So that's not true. Both trains speed up all the time. Well, that means that the magnitude of the velocity is getting bigger, and in fact, that's not true for either of them. For A, the magnitude of the velocity stays constant, and for B, the magnitude of the velocity gets smaller. Not true, B. Both trains have the same velocity at some time before TB. Well, that's definitely true, because TB was here, and we found that they had the same slope at some moment in time, which corresponded to here on the position graph. So that one is true. Somewhere in the graph, both trains have the same acceleration. Well, how do we find acceleration? Acceleration, A sub x, well, acceleration is delta Vx over delta t. So it's the slope of the velocity graph. Well, what's the slope of the velocity graph for A? Well, that one is just 0 at all time. Oops, that's for A. So A has a 0 acceleration because its velocity is not changing. B, the velocity is changing, and in fact, the slope is everywhere negative, right? Because it's getting smaller and smaller here. So you have negative values of the slope. The negative value is getting larger in the negative sense. So B is going to be something like maybe this graph here for the acceleration. So do they have the same acceleration? I don't think that they do. On my plot, it looks like they have the same acceleration at time 0. But that's because I drew this completely flat here, and there was no real good reason why that should be flat, because it's not like the slope was the same from one moment to the next. So I really should have probably drawn this one here like, oops, more like this, in which case you'll have some initial negative slope here, like that. And then they never have the same acceleration. But other than the moment in time at the very beginning, they certainly don't. That concludes our